In this video, we'll cover Bohr Rutherford diagrams, but first we'll start with a little joke. Now that we know about atoms and the structure of atoms, we can use this to tell a whole bunch of jokes. So, why can you never trust an atom? Because they make up everything. So, with Bohr Rutherford diagrams, so we've talked about the structure of an atom. An atom is made up of protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. Electrons are found in orbits around the nucleus. So there is a way in which we can represent the structure of an atom, and this is using a model put forward by the scientists Bohr and Rutherford. So these are diagrams based on what they came up with what an atom looks like. So the Danish physicist Niels Bohr derived the planetary model of the atom, and this is what the Bohr Rutherford diagram is going to be based on. In this model, electrons are arranged in orbits that surround the nucleus. So we'll have the nucleus at the center of our solar system here, kind of like our solar system. So, the sun is at the center of that solar system, so the nucleus is at the center, and then orbiting around the sun, orbiting around the nucleus, are those electrons, like the planets orbiting around a sun. So, in this model, he suggested that electrons move around the nucleus in orbits like planets moving around the sun. Each electron in an orbit has a definite amount of energy, and this is usually referred to as a quantum of energy. It has a defined amount of energy. So this definite amount of energy has implications for the movement of the electrons. So that definite energy means that they are found certain distances away, kind of like the planets away from the sun. And those electrons stay within those energy levels. So like, you don't have a planet that will leave its orbit. You don't have electrons that typically leave their orbit, although they can. He also suggested that the farther away the electron is from the nucleus, the greater amount of energy that electron will have. So electrons closer to the nucleus will have lower amounts of energy. Electrons further away from the nucleus will have higher amounts of energy. So those electrons further away from the nucleus will be more reactive, so more likely to leave. And it's when you have electrons leaving and coming in where you get chemical reactions that can happen. Electrons are more stable when they are at a lower energy, closer to the nucleus. So the closer an electron is to the nucleus, if it's closer in that orbit, then it'll be more stable. And electrons cannot exist between orbits. This is kind of a ramification of this part here, where electrons have a definite amount of energy. So you won't get an electron that exists in between these two orbits here. The electron is either here or it's here in this orbit or that orbit, not in between, not sort of next to it, not right in the middle, like it's in it or not in it. But electrons can move up or down from one orbit to another. So if an electron, is in this first orbit here, and there's room in that second orbit, the electron can move up into the second orbit. So it can gain energy, this energy needed to go up into the second orbit, and exist there for a bit. Eventually, it will lose that energy that it has gained and come back down to its original orbit. And then don't forget, within the nucleus, we find those protons that are positively charged and neutrons which have no charge. Don't forget that in a neutral atom, the overall charge on that atom is 0. So the number of protons is going to equal the number of electrons. So, how do you draw a Bohr Rutherford diagram? So you begin by drawing a circle. So you start by drawing a circle. This circle will represent the nucleus. You write down inside the circle the number of protons and neutrons inside that circle, which represents the nucleus. So, use the following short forms that we discussed in the previous video. The symbol for a proton is a lowercase p with a superscript plus sign. So if there are 11 protons in the nucleus, you would write 11p plus. The symbol for a neutron is n superscript 0. So if there are 12 neutrons, you would write 12n superscript 0. And then we would use circles or parts of circles for the electron shells. So those orbits, or electron shells, would be represented as circles around the nucleus. Or we could do a part of the circle. So we'll look at both diagrams here. And then just remember that number of protons is equal to the atomic number. Atomic mass is equal to the number of protons plus electrons. With the atomic number in a neutral atom, this tells you the number of electrons as well. So remember that neutral atoms have no charge. And so, the reason why that is, if we consider, for example, a nucleus that has 15 protons in it, protons are positively charged, that neutral atom will also have 15 electrons around it, and each electron carries a negative charge with it. So in total, there will be 15 positive charges in that nucleus or in that atom, and 15 negative charges in the form of electrons. And then, if you have plus 15 plus negative 15, because there's a 15 negative charges from those electrons, the sum of those charges is going to be 0. And this is what makes that atom neutral. When you start to change the number of electrons, increasing the number of electrons, this overall charge on the atom can change to a -1. And then if you decrease the number of electrons within the atom, this can change the overall charge on the atom to +1. So the charge on the atom can change depending on the number of electrons around the nucleus. So an electron is also shown as a small filled circle on a shell, so a little dot. Basically, the first orbit, and basically with these orbits as well, these energy levels around the nucleus, each orbit can hold a certain number of electrons. The first orbit, or the first shell, is the first circle surrounding the nucleus. It can hold a maximum of 2 electrons. So when you draw 2 electrons into that shell, you go 1, 2, and then that's it. That orbit is full. You can't put any more electrons into that first orbit. The second orbit is the second orbit is the second circle surrounding the nucleus. So if you have more than 2 electrons, you would draw 1 circle, put in 2 dots on the ring of that first circle, and then you would draw another circle and continue adding in electrons. So that second orbit can hold a maximum of 8 electrons. Once 8 electrons have gone into that orbit, it is now full, and if you still have more electrons to add, you would draw a third circle. That third circle would represent the third orbit, and is the third circle surrounding the nucleus. It can hold a maximum of 8 electrons. If we go beyond those 8 electrons, and then we draw another circle, so that fourth circle, which would be the fourth orbit, and as the fourth circle surrounding the nucleus, it can hold a maximum of 18 electrons. Once an orbit is full, you must draw another orbit and continue filling it with the remaining electrons. Typically, we won't go past calcium. in terms of drawing Bohr Rutherford diagrams, which is the 20th element on the periodic table. So some examples are shown here in terms of Bohr Rutherford diagrams that have been drawn. So for example, with sodium, first thing we would look to do is figure out the number of protons, neutrons, and electrons. So using a periodic table, you would find the symbol for sodium, which would be Na. You would find the atomic number, which would be the number of protons in the nucleus. And you could find the atomic number, or sorry, the atomic mass, and subtract from that the atomic number, and this will give you the number of neutrons. In sodium, the atomic mass is 23, the atomic number is 11. When you subtract the atomic number from the atomic mass, you get a number of 12, which is the number of neutrons. And in this case, I believe the atomic mass on your periodic table is 22.999. I just rounded up to 23. And then the number of electrons is equal to the atomic number, the number of protons. Once we have protons, neutrons, and electron numbers figured out, we can start drawing a Bohr Rutherford diagram. So first we'll draw a circle here that represents the nucleus. We will then write in the number of protons. So in this case, we have 11 protons, so we write 11p plus. We also write the number of neutrons, so we have 12 neutrons, so it's 12n superscript 0. And then we start adding in electrons. So in this case, we have 11 electrons that we need to add in. So we would draw one circle first around the nucleus. This was our first orbit here. We would draw a circle representing one electron, and then on the other side we would draw in a second electron. So electrons typically want to be as far apart as possible. They only pair up when they absolutely have to. So we have 1, 2 electrons. This orbit is full. We need to draw another circle, which is the second circle here. And then we can add in electrons. So when we add in electrons, we add in one at a time. So we add in 1 electron, 2 electrons, 3 electrons, 4 electrons. And then when we get to the 5th, this is when we start doubling up. So we draw in a 5th electron, 6th electron, 7th electron, 8th electron. Once we hit 8 electrons, this orbit is full, the second orbit is full, and we have to draw a third orbit. So when we draw that third orbit now, we still have 1 electron to go, so we just draw that one lone electron. And then here is the Bohr Rutherford diagram for sodium. We can also draw our Bohr Rutherford diagrams using half circles for the orbits. And we can use numbers to represent electrons. Our nucleus is drawn in the same way in which we draw a circle. And in this case, we'll use the example of fluorine here to come up with this drawing. So for fluorine, from the periodic table, fluorine has an atomic number of 9, so it has 9 protons, which means neutral fluorine will also have 9 electrons. The atomic mass of fluorine, I believe, is like 19 or close to 19, around 19, but when we round, we get 19. So when we subtract the atomic mass and the atomic number, we get 10, which indicates the number of neutrons. So we get 10 neutrons in the nucleus of fluorine. So we've written in our number of protons and our number of neutrons within the circle representing our nucleus. To add in the electrons in the half-shell model, you simply draw a circle and then partway through, you write in the number of electrons that you would find in the first orbit. So in this case, we know we're going to have 2 electrons in here, and then we're going to have to move on to a second orbit. So we can write in that number 2, and then use that short form for electrons, that E with a negative sign, to represent those 2 electrons. We still have 7 electrons that we need to add in, so we need to get up to 9 electrons. So we'll draw another half circle, and we know we have 7 electrons left. So we just write in that number 7 with that short form for electron, and then finish off our half circle. And this is the half circle method for Bohr Rutherford diagrams. On a quiz, test, exam, or whatever evaluation that you do, either form is acceptable, just don't mix them up. We'll have a look at also Bohr Rutherford diagrams for ions. So we've talked about Bohr Rutherford diagrams for neutral atoms, but atoms can gain or lose electrons. And when they gain or lose an electron, they gain a charge and they become an ion. So just recall that for a neutral atom, the number of protons is equal to the number of electrons. Atoms can gain or lose electrons to form charged atoms. The element is still the same because the number of protons has not changed. Remember, if you change the number of protons, you change the atom. If you change the electrons, you can change the charge. So in the following Bohr Rutherford diagram for lithium, we have 3 protons, 4 neutrons in our nucleus. Because we have 3 protons in a neutral lithium atom, there will be 3 electrons. So 2 in the first orbit, 1 in the outer orbit. When electrons get lost, it's always working out. It's always the outer atoms first, and then you work your way in if you were to continue losing electrons. But in this case, lithium is only going to lose just 1 electron. And when it loses that 1 electron, all that's left is that first orbit. We've gotten rid of this second orbit now. We don't need to draw that. And when we look at the sum of the charges in that lithium atom now, we see that we still have 3 protons, so 3 plus 1 charges. We now have 2 electrons, each with a -1 charge, and when we add those charges together, we are left with an overall charge of +1. We show that by writing square brackets next to the atom and then putting a +1. Fluorine is kind of the same idea. So here, lithium is losing an electron to gain a charge. In the case of fluorine, it could gain an electron and gain a negative charge. So when fluorine gains an atom and it has room for an electron in that second orbit, remember that second orbit can hold 8 electrons, and right now we have 7 electrons in there. So we have 2, 4, 6, 7. We can fit an 8th electron in there, so it can pick up an electron. And when it gains that 8th electron, it now has more negative charges than it does positive charges. So if we count up the number of negative charges, we would get 10 negative charges, whereas there are 9 positive charges in the form of protons in the nucleus, and this will give us an overall charge of -1. So why do atoms form ions? What is going on with this gaining and losing of electrons? Why does this happen? So the electrons located in the outermost orbital shell of an atom are called valence electrons. Those electrons hold special importance. It's because ions are formed because they are most stable or happiest when they have a full orbital shell of valence electrons. What that means is the outermost orbit that they have containing electrons, they want it to be full. If it's full, they're happy. They don't want to gain or lose anything. But if it's not full, they will look to either lose or gain depending on what is easiest. And so most elements will form ions by losing or gaining enough electrons to have 2, and this is in the first orbit, or 8 electrons in their outer orbital shell. So we go back to this example here of lithium. So this electron here, this third electron in that second orbit, this is considered the valence electron for lithium. Remember that in the second orbit, we can hold 8 electrons in that orbit, but lithium only has 1. So it's easy for lithium just to lose that electron, get rid of it. and just have the one orbit with 2 electrons in it. This is a full orbit, and lithium is happy with this full outer valence shell or outer shell of electrons now. So the losing and gaining of electrons can happen in 2 ways. So an atom can lose electrons, leaving it with extra protons, and therefore an overall positive charge. So as we talked about with lithium, a lithium atom becomes an ion by losing 1 electron. So again, here we have the neutral lithium ion. It will lose that outer electron. Just, it'll be lost. We can talk about where it goes. And now in orbiting that nucleus is just 2 electrons. So a lithium ion will still have its 3 protons with a positive charge, and those 2 negative electrons give it an overall charge of +1. The charge on the ion is equal to the sum of the charges on its protons and electrons. Lithium has 3 protons, 2 electrons. The sum of the charge is -1. The ion is represented as, and I know I have sodium +1 here, or Li1+. So you write the symbol for the element, Li, and then to indicate that it is an ion, in the top right corner, you would write the charge on that ion. So you could write it just as plus or 1+ in this case. An atom can gain electrons, leaving it with extra electrons, therefore attaining an overall negative charge. So a fluorine atom can become an ion by gaining 1 electron. So here we have that fluorine atom. Here is a neutral fluorine atom with 9 protons, 9 electrons, and its overall charge is 0. In that second orbit, once again, there are 2, 4, 6, 7 electrons, and 8 electrons can fit into that second orbit, so there is room for 1 more. So fluorine can gain that extra electron into its orbit, and this will now cause an increase in negative charges, leaving fluorine with an overall -1 charge, and this makes fluorine an ion. So this ion can be represented as F-1, or you can write it as F1 negative, or just F negative. The important thing is that the charge is placed on the upper right-hand side of the element symbol. So Bohr Rutherford diagrams for ions are drawn using the same rules as neutral atoms. They will have the same number of protons and neutrons as the neutral atom, but will have a different number of electrons. So they'll have a different number of electrons, a charge, and a full shell of valence electrons. So to determine the number of electrons in an ion, you use the following formula. So the number of electrons is equal to the number of protons minus the charge on the atom. So for example, with sodium, you'll notice there is nothing written here in the upper right-hand side, so that indicates it is a neutral atom. So it has no charge. So if we take the number of protons and subtract the charge, it tells us the number of electrons. So in this case, we have 11 minus 0, since it's neutral, for a total of 11 electrons. For sodium ion, that has a charge of +1, to figure out the number of electrons, we take the number of protons, which is 11, and subtract the charge, which is +1. So we have 11 minus 1, which gives us a total of 10 electrons. For something like fluorine, it would be the same thing. So for fluorine ion, we would take the number of protons and subtract the charge. So we have 9 protons minus a charge of -1. A negative times a negative becomes a positive, and we have a total of 10 electrons orbiting that nucleus. So using this way to figure out electrons, we can go about drawing Bohr Rutherford diagrams for ions. We figure out the number of protons in the same way, so it is the atomic number. Neutrons is calculated in the same way. It is atomic mass minus atomic number. And so for this case, for chlorine ion, the number of protons is 17. The number of neutrons is 18. To figure out the number of electrons, we take the number of protons, in this case is 17. We subtract the charge, which we're told is a -1. A negative times a negative is a positive, and we get